In today's video, I would like to introduce you a very nice problem of Swiss International Mathematical Olympiad Team Selection 1999, question number 5. Okay, here is the following statement: prove that product of 5 consecutive positive integers cannot be a perfect square. Okay, in the other word, if you pick up 5 positive consecutive integers and you make the product of those numbers, never be a perfect square. Okay, so that's our goal. We are going to prove this one. Go ahead, pause this video if you would like to give that try to this problem. When you are, come back to see the full solution. Okay, let's get into the solution now. Let's set P of n equals n is multiplied by n plus 1 is multiplied by n plus 2 and is multiplied by n plus 3 and lastly n plus 4. Okay, we have 5 positive integers here. We have 1, 2, 3, 4, 5. Okay, now we are going to prove this number is not a perfect square. Before we go over to the general proof, we are going to obvious cases. Let's take P of 1 is given as 1 is multiplied by 2 is multiplied by 3 is multiplied by 4 is multiplied by 5. This one is given as 120. So as we know, 120 is between 100, which is 10 square, and 121, which is 11 square. Okay, let's pick up another number. P of 2 is given as 2. This is for all n super equal to 1. This is for all n super equal to 2. P of 2 equals 2 is multiplied by 3 is multiplied by 4 is multiplied by 5 is multiplied by 6. Okay, this is the consecutive numbers. This one is given as 720. 720 is between 27 quinary square and 26 quinary square. Okay, if you calculate this one, is giving you something is approach to this one. So we take in the number less than this one, we take the quinary square. So we have 120 is between 2 consecutive squares, and we have 720 is between 2 consecutive squares. So that means is not perfect square. So that means 120 is not perfect square and 720 is not perfect square. Let's move on to the general case. This is for all n integer n. We have this following: P of n equals n is multiplied by n plus 1 factor n plus 2 factor n plus 3 and the last one n plus 4. I'm going to distribute this one to see what's the general expression for this one. So I have P of n. So I'm going to make the product of these two terms first, then I'm going to make the product of these two terms, then I will make the whole product. So for the first product, I will have n squared, this one by this one. N is multiplied by 2 is given as 2n plus n, which is plus 3n, plus last one plus 2 is multiplied by this product. This one is multiplied by this one is given as n squared plus 4n plus 3n, which is 7n, plus the last term 3 is multiplied by 4 is given as 12. Okay, then I'm going to make this product. This one is multiplied by this one is given as n to the 4th. This one is multiplied by this one is given as plus 7n cubed plus 12n squared plus this term plus 3n cubed plus this one by this one is given as plus 21n squared plus plus this one 3n is multiplied by 12 is given as plus 36n plus the last term. This one is multiplied by n squared is given as 2n squared plus 7n is multiplied by 2 is given as 14n plus the last one 2 is multiplied by 12 is given as plus 24. Now I'm going to collect n cubed term and n squared term and n terms, and so we'll have n is multiplied by n to the 4th. This one is 7n cubed plus 3n cubed is given as plus 10n cubed. For n squared I have 12 plus 21 is 33, plus 2 is plus 25, n square. For the n term, I have 36 plus 14, which is 50, plus 50n, plus 24. So this is the general expression. Now I'm going to make this expression on the form of the quinary square, okay? This one will be written on this form. So I have P of n, it will be written on this form, n square plus capital an plus capital B, quinary square. So in order to find a and b, I'm going to distribute this one and match the numbers, okay? So this one is giving us, by distributing this one, is giving us n square plus a is multiplied by n, quinary square. So I'm applying this identity. So by setting this one as a letter a and b as a letter b, we will have n square plus capital an, quinary square, plus 2 times b is multiplied by n square plus an, okay, plus 2 times capital A n cubed plus capital A square n square plus this term. So I'm going to distribute this one, is giving me plus 2 capital B n square plus 2 capital B capital A is multiplied by n plus the last one capital B square. Now I'm going to collect whatever the term has n square and the number has n. I'm going to put them together and match the numbers between left and the right hand of this equation, okay? I have P of n, I will have this one, n to the fourth plus 2 capital A n cubed plus this term plus capital A square plus 2b. I'm putting n square, I'm collecting these terms and put them together under n square with n square as a common factor. I will have n square here for n term plus 2 times capital B capital A, okay, and plus the last term b square. Now I'm going to match the numbers between this expression and this expression. So if you take a look carefully here, n to the fourth will be still the same because as a first term, n cubed, we have 2a equal to 10. We have 2 capital A equals 10, okay? In fact, there is a trick to find those numbers, capital A and B, without doing this calculation, okay? Because I want to go through the details, okay? So for the capital A, it's easier without doing this calculation, because capital A is always this number divided by 2 is giving us 5 without calculating it. For the second term, I will have capital square equals capital A square to B to capital B equals 35 and to BA equals 50, okay? So this one is giving us capital A equals 5, 10 divided by 2. For the B, we don't need this second expression. Going through the third expression will be easier to calculate it. This one to be A equal 50, that's mean I'm going to put 25 dividing both sides by 2. Now since I know the capital A equal to 5, that's mean I have 5 is multiplied by capital B is equal to 25. So by dividing both sides by 5, I will get capital B equals 5. Okay? Now I will have the expression of P of n equals n is multiplied by n square plus capital A we found equals to 5 n plus capital B equals 5 quinary square. Okay, so I'm going to clean up this board and bring this one at the top and continue with our problem. so from the last board, but I found this one equal to this one. But remember, this one is not true, okay? This one is not equal to this one, because if you distribute this one, is giving you 25. If you distribute this one, if you distribute n to the n square plus 5n plus 5, quinary square is giving us n is multiplied by this one the same, and to the fourth plus 10 n cubed plus 35 n square, but is giving you 25. Okay, here. So that means you have one number more than this one. In the other word, I put it on 24 plus 1. This term equals p of n. Okay, not plus 1. Okay, since we have p of n equal to this term, that means this term is a bigger than p of n. So it's telling us p of n is strictly inferior than this term. N is multiplied by n square plus 5n plus 5 quinary square. Okay, this one equal the same thing, but one more number up. Okay, this one is 24, the other one is 25. If you distribute this one, is giving us this one. So that means always p of n is strictly inferior than this one, this square. Then this one is strictly inferior than n is multiplied by n square plus 5n plus 4, by taking one number down. Okay, so since you have positive numbers, that means this one is always less than this one. So in order to make the comparison between this one and this one, just simply distribute this one out and make the difference between these terms. You will find the difference is strictly inferior than 0. Since this one is clear enough, is smaller than this one, because we taking one number less, that means is arithmetically this one is strictly inferior than this one. So without proving it. Okay, we have n as an integer, but this is not square. So in order to complete the square here, so we have to put the square root of n, then put this one like this, square root of n. So we have two contradictions here. So in order to have this one as a perfect square, you must have square root of n a perfect square as well. So this one is not happening for every positive integer n. It could be happen for one, for the other one it will be not verified. Okay, for example, if you take the n equal to 2, you will have square root of 2. So this is not perfect square. The second contradiction, we have two consecutive squares. We have p of n is located between two consecutive squares. Okay, so p of n is between two consecutive squares. Finally, n cannot be a perfect square. So I have done with this problem. If you are interested in watching this one, don't forget to support us with your like and subscribe. Thank you for watching. I will see you in the next video. Bye.